so if we look at this on an energy level diagram, this becomes a little bit easier to understand. And so we draw this energy level diagram by noting that the light is being scattered off of a virtual state. So that virtual state is really like the polarized electronic environment, right? It's those distorted MOs, okay, that create what we call this virtual state. And so now the Rayleigh line, right, is just simply if we're using one color, right? So this is assuming one color, right? Then there's no change in that effect, okay? And so here you can see a spectrum of intensity versus Raman shift. And if we were using 532 nanometers, right, as our incident radiation, then for the Rayleigh scattered line, lambda 1, the scattered wavelength, is going to come out right at 532. And this will be the most principally observed light. And what I also want to point out, when I draw a little, I'm going to draw our little detector here, okay? And our detector is detecting visible radiation. It is looking for that 532 or thereabouts wavelength, all right? So that is as you can see, that 532 peak, I mean, it blows out this scale. So typically you would use a filter to block out the 532 wavelength. So block out 532, okay? So now, what is the deal with this Stokes shift? All right, well, if we scatter that incident radiation off the electronic environment, and when it relaxes, if it relaxes down to a higher rotational level, or it could be a higher vibrational level, right? In terms of J's, it's got to be plus minus 2. But in terms of vibration for the Raman effect, right, it's just plus minus 1, okay? So if this were vibrational Raman, I would replace these J's with nus, and this red line would go down to the nu equals 1 state. So in other words, it's leaving the molecule in an excited state, okay? And so what that means is that Stokes light that comes off, right, the Stokes shift, is going to be less than 532, right? Just based on the size of this, right? So if I ID this as lambda 0 and this is lambda 1, you can see now to look for the Stokes shift, I would set my detector to look for wavelengths less than 532 nanometers, right? Because of that diagram. However, I'm also at the same time going to be getting anti-Stokes shifts, where, in other words, because now I've left a molecule in an excited state, or because of just simply its rotational population of states, right? If this is the rotational lines, then, right, these molecules exist in these higher lying levels. And in the case of vibration, well, the Stokes shift puts it in an upper lying vibrational level, okay? So anti-Stokes starts at a higher level, and the result is that a bigger energy comes out, okay? So you can see in the anti-Stokes, right, those all look like, negative numbers, whereas in the Stokes, they look like positive numbers. And so here's how we calculate those Raman shifts. And so I've got it here coded up, and I think I actually need to put 530 in there. So let's suppose that, just kind of playing around with this. So let's suppose we shine some 532 nanometer light on our molecules, okay? And then we detect that Stokes shift. So we detect something at 530 nanometers, let's suppose. So what is it that could have given us that 530? And I'm just pulling those numbers off the top of my head, right? I'm just saying, suppose 532 comes in and we detect a 530 nanometer photon going out. Well, if I calculate that Stokes shift, which would go 1 over 532 minus 1 over 530. And so let's take away that factor 10 to the 7, because that would be 1 over nanometers. So I get this crazy number, negative 7 times 10 to the minus 6 inverse nanometers, right? So let's say that's negative 7.09 times 10 to the minus 6, 1 over nanometers is the way that's going to work, right? Well, we know there's 1 times 10 to the 7 nanometers in 1 centimeter, right? So if I multiply this by a factor of 10 to the 7, that's going to put that in units of wave numbers, okay? So that means that if I detected that 2 nanometer difference, then that means I would have had to have, that's wave number. That means that there would have been some vibrational or rotational, but based on these numbers, 70 wave number, that's a vibration. So vibrational normal mode. That's exactly what would have resulted in detecting that 2 nanometer shifted photon, that there was some vibrational mode at 71-ish wave number, okay? Which is pretty cool. And so, of course, in the Stokes shift, right, because this graph is actually showing us vibrations, just, again, based on the Raman shifts, okay? Then I would see the corresponding positive peak, which is also kind of cool, right? And so typical, Raman shifts, they're going to correspond to the vibration. So we're going to see Raman shifts that are like, a couple thousand wave numbers, okay? So here's a great example. So here is the IR spectrum of CO2, right, where we're seeing new asymmetrical and we're seeing new bend. Well, as it turns out, neither of those modes are Raman active because they don't disturb the electronic environment enough. However, the new symmetric stretch is Raman active, right? And recall we said that, that one is at, so let's back up here and let's put some labels on these, right? So the 667 and 2349, so that's 667, and this one's 2349. But that symmetric stretch would occur at, it was 13 something. 1388. Okay, so that one is Raman active. So this is really cool about the Raman effect or Raman spectroscopy, is that we can observe modes that might not be observable in FTIR. Here's another great example of the Raman shift for benzene versus the FTIR. And you can see that there are some peaks that match up and some peaks that don't. So some of these peaks are Raman active, some of them are IR active. Okay, so these serve as great diagnostics when you can do both Raman and IR. Sorry, I'm just checking my time here. Then you can get a really nice positive ID on a molecule, especially if it's a molecule that hasn't ever been synthesized before. If it's a brand new molecule, you might not be aware of all of the active FTIR modes or Raman modes, right? Or, as I alluded to earlier, if it's a complex arrangement of molecules, perhaps it's some novel phase, right? Or some novel arrangement. Doing both techniques would give you an ultimate characterization of the molecule. Okay, so let's move